In this section, we'll talk about another proof of the quadratic reciprocity law. This proof is due to Eisenstein, and it is more elementary in the sense that it uses less abstract algebra. But at the same time, it is more technical. The proof will be based on two lemmas. The first lemma is a lemma due to Gauss. Now let us state it. Let P be an odd prime, meaning a prime number bigger than 2, and let S be a subset of Fp star, the multiply group of the finite field Fp with P elements. Let S be a subset of Fp star such that Fp star is a disjoint union of S and minus S. Or we can write Fp star equal to S disjoint union minus S. Here, the set minus S consists of elements of S multiplied by -1. Namely, you take the additive inverses of elements in S. So that is our minus S. In the following, we shall take S to be a special subset. We simply take S to be the first P minus 1 divided by 2 elements. 1, 2, all the way to P minus 1 divided by 2. Now we are going to introduce some new notations. If little s is from this S and little a is from Fp star. And if we take the product of A and S, so if you look at A times S, this is still an element in Fp star, but this product may no longer live in S, because Fp star is a disjoint union of S and minus S. So this product is either in S or in minus S. And we write this as E sub S of A times S sub A, with E sub S of A is plus or minus 1, and S sub A in S. Namely, we still want to put this A times S into S, but we need to pay a price. If necessary, we're going to subtract a minus 1 from this product to make sure this guy still lives in S. So we write A times S as E sub S of A times SA, where SA is always in S. And I want to emphasize that E sub S of A and SA are uniquely determined by A and S. There's no ambiguity on the right-hand side. Why is that? This is because if you try to write A times S in two ways, on one hand, if it is equal to 1 times SA, but on the other hand, it is equal to minus 1 times some SA prime. In this case, where SA and SA prime are both in S. In this case, we're going to get SA plus SA prime equal to 0 modulo P. However, this is impossible because we have taken S in this form, so their sum is at most p minus 1. This is at most p minus 1 divided by 2 plus p minus 1 divided by 2. So it cannot be congruent to 0 mod p. This is a contradiction toward construction of S. Therefore, this E sub S of A and S sub A are uniquely determined by A and S. And now we can state and prove Gauss Lemma. The Gauss Lemma states that the Lagrange symbol of A modulo P is equal to the product of E sub S of A for S ranges over S, where this E sub S of A and capital S are defined as above. And let me still recall the definition for the Lagrange symbol. By definition, this is a to the power p minus 1 divided by 2 in the finite field Fp. And S is a subset of integers 1, 2, all the way to p minus 1 divided by 2. And now let's prove Gauss Lemma. We first remark that the map sending S to S sub A is a bijection of S onto itself. Let me write this as a claim. Now let's verify this claim. Since S is a finite set, it suffices to check that this map is an injection. Indeed, if SA is equal to S prime A, where SA is the image of S and SA prime is the image of S prime, then we have A times S equal to E sub S of A times S sub A. S sub A is equal to S prime sub A. And if we write E sub S prime of A in the front, then we know these two products may or may not be equal, but they only differ by a plus minus sign. And if we continue with the right hand side, we get plus minus A times S prime. So we obtained that A times S is equal to plus minus A times S prime. This implies S is equal to plus minus S prime. Remember that S lives in capital S, and S consists of integers 1, 2, all the way to p minus 1 divided by 2. And S prime also lives in here. It follows that S equal to minus S prime is impossible, because S is less than or equal to p minus 1 divided by 2, and S prime is also less than or equal to p minus 1 divided by 2. So S plus S prime is less than or equal to p minus 1. So S plus S prime cannot be divisible by P, because S is between 1 and P minus 1 divided by 2, and S prime is also between 1 and P minus 1 divided by 2. So S plus S prime cannot be 0 modulo P. So the only possible situation for this to be true is that S is equal to S prime. And this verifies this claim. Now we have shown that the map sending S to S of A is a bijection. How do we make use of this? We consider the equalities AS equal to ESA SA for S in capital S. And we multiply these equalities on both sides for S ranges over the whole S. On the left-hand side, because S has cardinality P minus 1 divided by 2, if we pull out the a's, we get A to the power P minus 1 divided by 2. And the rest is the product S for S ranges over capital S. And the right side is a product of ESA's and SA's. And now, because our claim that the map sending S to SA is a bijection, it follows that this product is equal to this product. The factors here are just a permutation of the factors here. So they are equal. And this product is also non-zero, because it is equal to P minus 1 divided by 2 factorial. So this product's coprime to P, and thus cannot be equal to 0 modulo P. So it is safe to cancel this thing from both sides. And we conclude that A to the power P minus 1 divided by 2 is equal to the product of ESA's for S ranges over capital S. But the thing on the left-hand side is precisely the Lagrange symbol by definition. And this proves Gauss Lemma. Now let us use a concrete example to illustrate the power of Gauss Lemma. We will recompute the Lagrange symbol of 2 modulo P. Remember, we did this for theorem 5 on page 7. And now we'll use Gauss Lemma we just proved to compute this guy again. To do this, we take little a in the Gauss Lemma to be 2. And as before, S is a set 1, 2, up to P minus 1 divided by 2. And for this A and the element S in here, ES2 can only be plus 1 or minus 1. And this is plus 1 precisely if 2S is less than or equal to P minus 1 divided by 2. Here, 2 plays the role of A. And if 2S is bigger than P minus 1 divided by 2, then we get negative 1. Now by Gauss Lemma, we have the Lagrange symbol of 2 modulo P is a product of ES of 2 for S ranges over capital S. And this is equal to some power of -1. We put the exponent n of p here, where n of p is the number of integers s such that 2s is bigger than p minus 1 divided by 2. Or in other words, s bigger than p minus 1 divided by 4. And the largest possible number for little s is p minus 1 divided by 2. So now let us count how many integers are there satisfying these inequalities. We'll talk about this in two cases. Note that p is an odd prime. P is odd. We have two cases. First, if p is of form 4k plus 1, then p minus 1 divided by 4 is equal to k. And p minus 1 divided by 2 is equal to 2k. It follows that there are precisely k many integers satisfying this. This implies n of p is equal to k. And second, if p is of the form 4k minus 1, where k is an integer, then p minus 1 divided by 4 is k minus 1/2. And p minus 1 divided by 2 is 2k minus 1. And this implies n of p is still equal to k. Because the number of integers strictly bigger than this and less than or equal to this are the integers k plus 1 all the way to 2k minus 1. And if you count them, they are precisely k many. So n of p is equal to k. This tells us n of p is equal to k as long as p is an odd prime. And now let us rewrite these two cases in a different way. Let's look at what happens when you mod p by 8. Now remember, by theorem 5 on page 7, we compute this guy as 91 raised to the power omega p, where this omega p is p squared minus 1 divided by 8 modulo 2. So now let us connect these two cases to our previous theorem 5. So from here we get 91 raised to the power k, where k is from here. And depending on the parity of k, we have two cases. P congruent to plus minus 1 modulo 8 happens if and only if p is equal to 4k plus minus 1 for k even. And in this case, n of p, which is k, is even. And at the same time, p squared minus 1 divided by 8 is also even. In the second case, p congruent to plus minus 5 modulo 8 This happens if and only if P is equal to 4k plus minus 1 for k odd. If and only if n of P equal to k is odd. And this happens exactly when P squared minus 1 divided by 8 is odd. And we have recomputed the Lagrange symbol of 2 modulo P using the Gauss Lemma.